Hello everyone, welcome back to my channel. It has been some time since I uploaded my last video, and during this time I have been busy with my research as well as making progress in programming QuantumVITAS. So in this video I would like to show you the recent development progress, and QuantumVITAS has actually become quite advanced now that I'm going to show you. Okay, so this is the user interface as I have shown last time, and we could start a new project, let's say water, and now I have added a scale bar here. Yeah, you see that one segment here equals 1 angstrom, and then we could basically use a simple cubic and 10 angstrom as the box, and we put the molecule in the box. Let's use angstrom. First we want to put the oxygen atom at the origin and then the hydrogen atom at, for example, 1 angstrom in the x-axis, and the second hydrogen 1 angstrom in the y-axis. Yeah, of course this is not the correct structure because the angle is 90 degrees, but for water molecule it should be wider. To get the correct structure we need to do a relaxation calculation, and then we could add optimization here, and this is the optimization calculation. You have the geometry, and this is self-consistency. There are many parameters, but what you can do is to reset all to default. Yeah, and then the K point for the molecule in the box, we only need gamma point calculation. For the optimization we could also set everything to the default, so you don't have to worry about anything. If you want, we can lower the convergence energy, so make it more precise, and this is very easy. We could show the input, and this would be the input file, and we could run the calculation actually here. Yeah, you see that now it's running, and we go to we can toggle the geometry and the input output files, and those are the input and output files. Yeah, you could go to here, and this is the plot of the optimization energy convergence. Yeah, you see that it's going down and it's converging, and we just wait a little bit, and now the job is finished. It says idle, and we have different possibilities to analyze the data. We could show the information, so those are the information that is extracted, what is the last position, last cell parameters. We could also view the raw text. This is the standard output file, and we could also open it with System Explorer like here, and then we could plot the 3D geometry here. Yeah, you see that now this is the first geometry that is 90 degrees, and then we could go next, and you see that now it widens up. Yeah. Okay, so here I have shown you the optimization calculation. What I have also implemented is the self-consistency calculation, optimization calculation, dense state calculation, molecular dynamics calculation, and also TDDFT calculation. Yeah. So now I would like to show you how to do a dense state calculation. We do a new project, let's say silicon. We here use FCC lattice. The lattice constant is around 5.4 angstrom. And we could add the silicon here as 0, 0, 0, and 0.25, 0.25, and 0.25. Yeah. Remember that here I have a feature that we can change the primitive cell to actually the unit cell here. Yeah, and you see that this is the silicon crystal structure. Now I would like to add a dense state calculation. And also I would like to reset all to default, so we don't have to worry about anything. The K point density, let's say 666, and then in the non-self-consistency calculation we could change that to a bit higher, 8 by 8 by 8, but we change the smearing to tetrahedra, and in the dense state calculation everything is basically by default. Yeah. So we show the input, and this is the input for the self-consistency step, non-self-consistency step, and this is the dense state step. So we run the calculation. To check the input-output file, remember that we can toggle it here, and in this folder, that is the calculation folder, we have all of the files here. Yeah, And now everything is ready. Okay, we could refresh and then go to the denser state plot, yeah, and see that this is the denser state of silicon. We could show it without a marker, and this is the Fermi energy, which is located inside the gap here. Okay, so in this video I've shown you how to do geometric optimization calculation of water molecule, as well as the denser state calculation of silicon by QuantumVITAS. So you see that it's quite easy to use, and I hope that I can finish the early access version in July, and then I'm open to suggestions from all of you. So thank you for watching. I always appreciate your support by liking or subscribing to my channel, as well as starring the QuantumVITAS repository in GitHub that I will put in the description below. So thank you for watching, and I hope to see you next time.